In this unit, we're going to look at the relationship between the structure of an organic molecule and its relative acidity. In the last segment prior to this, we used pKa tables to assess the relative acidity of different molecules. And pKa tables are great, but we're going to run into a huge number of different situations where we're going to be faced with chemical reactions and trying to predict the products of those reactions and what types of acid-base chemistry is going to go on there. And in order to make those predictions, we're going to be able to pick out of those complex structures, where is the most reactive location? Where is the strongest acid, the most easily lost proton within a complex organic molecule? Most of the time in those situations, we won't be able to simply use a pK table in order to predict what the strength of the acid is. And so it's really important to be able to relate the structure of an organic molecule to its relative acidity. And that's going to be the goal of this discussion, is to enable you to relate the structure of a molecule to how reactive it's going to be. In other words, how strongly acidic is it going to be? Because remember that we use the term strong acid in reference to an acid that's really reactive, an acid where the reaction is going to go nearly to completion, so that this equilibrium arrow here would be very, very far toward the side of the products and very little reactant left at equilibrium. So as we look at our general acid-base reaction here on the screen, we defined our acid and base there on the left-hand side of the equation. Acid, of course, is our proton donor. Base is our proton acceptor, and the base is going to gain a proton during the course of the reaction. As a result of gaining that proton, the base becomes what we refer to as the conjugate acid. On the other hand, the acid loses a proton to become what we refer to as the conjugate base. So we're looking here starting from the left-hand side of the equation with our acid and base. And what's going to be the case is that the more stable the conjugate base product, that is, the more stable the product side of the equation, the further the equilibrium is going to lie toward the right. And that's no surprise, because if we have something that's really stable on one side of the equation and really unstable on the other, the side that's going to be most favorable is going to be the stable side, because the stable side is the lower energy side. That's the lazy side of the equation. That's where we would prefer to generally be. So the equilibrium to the right, meaning that the conjugate base product is really stable, will imply to us that the acid that we started with is a relatively strong acid. So when we look at this general acid-base reaction, if we see that this product side, our conjugate base, is stable, and the acid side is unstable, that's going to imply to us that the reaction equilibrium is going to lie very much toward the side of the product. So if we're looking at a molecule, we're trying to predict where a proton is going to be lost from that molecule, we want to remove a proton from the acid at the location where the product resulting from that will be the most stable possible conjugate base. And the more stable that conjugate base product, the further the equilibrium of the reaction we've shown up top is going to lie toward the right-hand side. So an equilibrium to that right-hand side with an unstable acid is going to refer to an acid where the pKa value of that acid is pretty low. It's a strong acid. So the lower the pKa value of the acid, we see up top there, the more stable the conjugate base product that results from that acid-base reaction will be. In other words, the equilibrium of these reactions are going to favor the side of the weaker acid and the weaker base. And in order to assess that, what we can do is we can look at the relative stabilities of different conjugate bases that are possible from a reaction to predict where a proton will be lost during the course of the reaction. Or if we're trying to look at this equation and decide which side the equilibrium is going to lie on, we could compare the relative stabilities of the base and the conjugate base here. And whichever one of those is more stable is going to refer to which side of the equation the equilibrium is going to lie on. So what we're going to learn here are some tools to predict the relative stabilities of different conjugate bases, because the more stable the conjugate base, the further the equilibrium is going to lie toward the product side. And furthermore, that can allow us, within a molecule has multiple different protons that could be removed, it allows us to predict which proton should be removed, because we want to remove the proton such that we will yield the most stable possible product out of that reaction. We're going to go through a list now then of factors that will stabilize conjugate bases, because our rule here is that the more stable the conjugate base, the further the equilibrium of the acid-base reaction will lie toward the side of the products. So we're going to answer the question here of what stabilizes the conjugate base. We're going to go through a list of a few different criteria that will act to stabilize the conjugate base. And by stabilizing the conjugate base, help push that equilibrium toward the side of the products. And by pushing the equilibrium toward the side of the products, the implication there is that that is going to be corresponding to a stronger acid reactant. So strong acid reactant leads to stable conjugate base product. So let's go down through the list here of different criteria that are going to act to stabilize the conjugate base, and we'll do an example of each one as we go along. So first off, on this list of items that we're going to plug in for stabilizing a conjugate base, having the negative formal charge on the more electronegative atom will make a conjugate base more stable, or even better than that, if we can create a conjugate base that's no formal charge at all, that's going to be stabilizing. So stabilize the conjugate base by placing or having the negative formal charge, so negative Fc for formal charge, on a more electronegative atom. Because a more electronegative atom is better able to handle that negative formal charge and remain in a relatively stable state. Even better than having the negative formal charge on a more electronegative atom is having no formal charge. So in some cases you can create a conjugate base that has no formal charge. And if we can create a conjugate base that has no formal charge, that's going to generally be more stable than situations where the conjugate base does have a formal charge. So let's do an example of that, where we're going to look at and compare the relative pKa values that we would predict for an alcohol, CH3OH. So we're going to ask the question of which is more acidic, or in other words, which has a lower pKa value, CH3OH or CH3CH3. So in each of these two cases, what we need to do is write out what conjugate base would result from deprotonating each of these two acids, and then we'll compare the stabilities of those conjugate bases. So we'll start with CH3OH. So our CH3OH, and I'm going to show that one bond to the hydrogen explicitly there so that we can show that proton, the hydrogen, being removed. We're going to react with a base. I'm just going to fill in generically B- as our base here. I'll show my equilibrium arrow. And then we'll do CH3, ethane. And I'm going to show one of those bonds to carbon, between carbon and hydrogen, explicitly there, because we're going to be breaking that carbon-hydrogen bond, and I want to be able to show that process taking place. So what we'll do now then is we'll take our electron pushing arrow from the base, bring it over, form a bond to the proton from our CH3OH, which acts as our acid. Bond between H and O breaks, and the electrons from that go onto the oxygen. And we'll go ahead and write out our conjugate acid and conjugate base here. So our conjugate acid is BH, our conjugate base is CH3O-. Fill in my lone pair electrons there just to dot all my I's and cross all my T's, so to speak. We come down here to our reaction of ethane with our base. Our base comes over, uses its lone pair of electrons to grab that proton from ethane. That forces the carbon-hydrogen bond to break here, and the electrons from that bond to go on to the carbon. So we'd end up again with BH, and we'd end up with CH3, CH2, and then notice that our covalent bond between carbon and hydrogen is breaking, and we showed the electrons from that bond going onto the carbon, so therefore carbon has to have a lone pair of electrons, and as a result that carbon is going to have a negative formal charge because that carbon has a lone pair of electrons plus 3 covalent bonds in total, which would give it a -1 formal charge. So asking the question of which is going to be more acidic, methanol, our 1-carbon alcohol, or ethane, our 2-carbon alkane, we see that by placing the negative formal charge on the more electronegative atom, that's going to lead to a more stable conjugate base. So we need to compare our conjugate bases here. So our conjugate bases are CH3O- and CH3CH2-. One of them has a negative formal charge on an oxygen. One of them has a negative formal charge on the carbon. If we look at the periodic table, oxygen is further to the right, therefore it is more electronegative. And so therefore, CH3O- is more stable. So this is the more stable conjugate base than having CH3, CH2- as our conjugate base. So we want to go with CH3O- as being the more stable conjugate base. It's the more stable of those two structures. And therefore, what that's going to correspond to is that our starting alcohol, CH3OH, is going to be the stronger acid, because the stronger acid gives way to the more stable product. So our stronger acid, or we could describe this as the lower pKa acid, would be another way to describe that. So certainly alcohols are going to have a lower pKa value than our alkane shown below, because the product that would result from deprotonating the alcohol is much more stable than the product that would result from deprotonating an alkane. So this illustrates how placing the negative formal charge on the more electronegative atom is preferable for stabilizing a conjugate base. We can go down to the second item on our list now of factors that will stabilize conjugate bases. And the second factor that we're going to talk about for stabilizing conjugate bases is going to be having the negative formal charge on the larger atom for atoms that are in the same group of the periodic table. So this particular guideline, as we go through different ways to assess the stabilities of conjugate bases, is going to apply only to atoms that are in the same column of the periodic table. If the two atoms aren't in the same column of the periodic table, then the electronegativity issue in point 1 is more important, and so you don't have to consider atomic radius. But in the case of atoms that are in the same group, that is the same column of the periodic table, having the negative formal charge on the larger atom is going to create a more stable conjugate base. So we'll add the caveat here that we're looking at for atoms in the same group, meaning the same column, having the negative formal charge on the atom with the larger atomic radius is going to stabilize the conjugate base. And if you look at the trends of atomic radiuses, when we think about atomic radii as we go down the periodic table, the atomic radius increases. So therefore, placing the negative formal charge on a larger atom lower down in the periodic table is superior to placing the negative formal charge on an atom that is higher up in the periodic table. So remember that that applies only to atoms that are in the same group. So don't make the rookie mistake of choosing two different atoms that are in different columns of the periodic table and trying to use this atomic radius comparison. If the atoms are in different columns, then instead electronegativity from point 1 up top is what you're going to go with. But if they're in the same group, meaning in the same column, place the negative formal charge on the atom with the larger atomic radius to give the most stable conjugate base. So let's do an example of that. And an example that we could look at for that is we could compare the relative acidities of, say, HF and HBr. So we're going to ask the question of which is more acidic, or in other words, which has the lower pKa value. So which is more acidic? We ask the question, HF, hydrofluoric acid, or HBr, hydrobromic acid. And in order to evaluate this, we need to look at the conjugate bases that would result from deprotonating each of those. So if we deprotonate HF by reacting it with a base, much like we did up top, the conjugate base that would result from that is going to be F-, fluoride anion. And the other conjugate base resulting from deprotonation of HBr is going to be Br-, our bromide anion. And since these two are in the same column of the periodic table, they're in the same group, we want to place the negative formal charge on the atom that has a larger atomic radius to give increased stability. And so based on that information, since bromine is further down on the periodic table, it has a larger atomic radius, and therefore it is going to be more stable as that anion. So larger atomic radius is going to give the more stable anion. And the way that you can think of this is, as we move down the periodic table, by increasing the atomic radius, the electrons have more space to spread out. And if they have more space to spread out, that's going to help minimize the repulsion between electrons and therefore help lower the energy of the system. So we're going to look at bromine as being the more stable of the two anions, and therefore the stronger of the two acids would have to be HBr because the stronger acid is what leads to the more stable conjugate base. So therefore, HBr is going to be our acid that has the lower pKa, or in other words, the stronger acid out of HF and HBr. All right, on to the next question, or next item that will act to stabilize a conjugate base. So we're going to go ahead to step point number 3 here on our list of factors that will stabilize conjugate bases. And item number 3 on the list, as a way to stabilize the conjugate base, is going to be if we can use resonance to delocalize a negative formal charge, that's going to greatly increase the stability of the conjugate base. So our third item on the list is going to be resonance delocalization. When we say delocalize, we mean sharing or moving the negative formal charge around from one atom to another by showing resonance structures. So third item is if we can delocalize or share the negative formal charge over multiple atoms by resonance, that's going to improve the stability of the conjugate base. And the way that you can think of this is if you can share the negative formal charge over multiple atoms by drawing different resonance structures where the negative charge moves from one atom to another in those different resonance structures, what that means is that no one atom is stuck with the full burden of carrying around a negative formal charge. Instead, the load is shared over multiple atoms. And much like if you were trying to carry a really heavy object, it's much easier to do it if you hold one side of the object and your friend holds the other side. Same thing is true here with resonance. Resonance allows that burden of the negative formal charge to be fully shared over multiple atoms. So let's take a look at an example of where resonance comes into play as a factor that governs the relative strengths of two different acids. So we're going to take a so-called carboxylic acid, which is a molecule of the COOH group. So we'll do CH3, carbon atom here, and OH, like so. So this is our acetic acid molecule. And we're going to compare that to ethanol, CH3, CH2OH, trying to predict which of these two molecules is going to be the stronger of the two acids, which will have the lower pKa value. So what we're going to do in each case is we're going to write out the conjugate base that would result from deprotonating each of these two acid candidates. So we'll take each and we'll react with the same base. So we'll do B- with a lone pair of electrons. B- with a lone pair of electrons over here. We're going to bring in our lone pair of electrons, come over, grab a proton from the carboxylic acid, make that oxygen-hydrogen bond break, and we'll write out the conjugate base that would result from this reaction. I'm going to show this as an equilibrium arrow here. So we'd end up with our conjugate acid being BH, which we're not really concerned about here. We're comparing the stabilities of our conjugate bases. Our conjugate base is CH3, and that CH3 connects to our carbon-oxygen double bond, and then over to an oxygen. That oxygen has two sets of lone pairs to start with. It picked up a third set of lone pairs during the reaction because we showed that electron pushing arrow breaking the oxygen-hydrogen bond and moving those electrons onto the oxygen. And then that's going to result in it having a negative formal charge. So we're going to write that out as well. We can come over and do a similar process with our alcohol molecule, taking the lone pair electrons from the base, bringing those over to grab a proton from the acid, break the oxygen-hydrogen bond, and we're off rocking and rolling with writing out the conjugate base of that CH3, CH2O- as the conjugate base. Conjugate acid would be BH. So now we need to compare the stabilities of these two conjugate bases. So we have the conjugate base resulting from deprotonating the carboxylic acid. We have the conjugate base resulting from deprotonating the alcohol. So whichever one of these two conjugate bases is more stable is going to correspond to what acid starting material was the more reactive acid, because it's going to give way to a very stable conjugate base. So we look at these two structures, and if we use the first couple of criteria from our list of ways to distinguish between the stabilities of different conjugate bases, we see that they both have a negative formal charge on the oxygen, and so we're not able to use any of those first two criteria to distinguish between these two. But what we can use is we can look at whether either of these two is able to engage in resonance to share the negative charge across two atoms. And in order for resonance to be productive here, to create a relatively stable conjugate base, it has to be able to allow that negative formal charge to be shared over multiple atoms. If the resonance structure you draw doesn't allow the negative formal charge to be moved over multiple atoms, shared over multiple atoms, then it's not going to be productive resonance in terms of stabilizing the conjugate base. And we're asking the question here, can we stabilize the conjugate base? So we take a look at our structure on the left, that is our carboxylic acid that's been deprotonated. And what we would see is that we can take this lone pair of electrons and we can move that over toward the left to make a carbon-oxygen double bond. And as we do that, in order to avoid going over the octet rule for the carbon, we can move the pi bond from the carbon-oxygen bond up onto the oxygen. And that's going to allow us to create a second resonance structure here. And we'll take a look at that second resonance structure that we can draw here and ask ourselves, would this resonance structure be productive in terms of sharing the negative charge over multiple atoms? So once we draw the resonance structure, we have still two sets of lone pair electrons that are bonded to that oxygen. Our third set of lone pair electrons became the pi bond that I'm showing in red. And then coming up to the oxygen up top here, we no longer have a double bond, we have a single bond because one of those sets of pi electrons moved up onto the oxygen. Now if we look at the position of the negative formal charge, the negative formal charge is going to have to reside up on that top oxygen atom. So we do have, with the case of the carboxylic acid that's deprotonated, we have the opportunity for that negative charge to be shared over two different atoms. And the more atoms we can share that negative formal charge over, the better. And in this case, that sharing of the negative formal charge is particularly favorable because of the fact that in both cases, the negative charge is on the most electronegative atom in the molecule. In both cases, the negative charge is on an oxygen atom. This would be less favorable if the negative charge is being shared between, say, an oxygen and a carbon atom, because the carbon isn't as electronegative, and so it isn't as able to carry around that negative formal charge. But here we've got the best case scenario, really. We're sharing that negative charge over two pretty electronegative atoms, over two oxygen atoms. So this is going to be resonance that definitely helps improve greatly the stability of the molecule. On the other hand, if we come over and we look at our conjugate base for our alcohol, and I'm going to go ahead and try to draw a resonance arrow here and maybe write some resonance structure. So I'm going to do my resonance arrow. Remember, that's the single arrow that has two heads, not to be confused with an equilibrium arrow. So our resonance arrow we have drawn in, and we think about ways to draw resonance structures. So this is a covalent bond there connecting the oxygen and the carbon. And you might be thinking, okay, well, can we move the lone pair electrons over to make a carbon-oxygen double bond? Because remember that in resonance, the only thing we can move are pi bonds and lone pairs. We don't have any pi bonds here. All we have are lone pairs. So we're trying to move that lone pair over, but if we made a carbon-oxygen double bond there, it's game over because our carbon right here would end up going over the octet rule. We can never go over the octet rule. So therefore, that electron pushing arrow set just isn't going to work. There's going to be no opportunity for resonance here. There's no second resonance structure that you can draw to show that negative formal charge being shared over multiple atoms. And so as a result, the conjugate base on the left is going to be the more stable because of the fact that resonance allows each of those oxygen atoms to essentially carry just half of the negative formal charge burden rather than the whole burden, because we can write those two structures showing the negative charge being delocalized. Delocalized meaning spreading out, meaning it's being shared amongst the two. So this is a really great example of how we can use resonance as one of our resources to predict the stabilities of molecules, in this case, predicting the stabilities of these conjugate bases. The next item on our list of ways that we can go about stabilizing the conjugate base is going to be through a phenomenon called induction. When we talk about factors that stabilize and destabilize organic molecules, two of the biggest players are going to be resonance and induction, where resonance is generally going to be the more important of the two. Induction is going to take second place in terms of stabilizing or destabilizing a molecule. So in this case, we're looking at ways to stabilize the molecule. And when we talk about induction as a way of stabilizing a molecule, the delocalization of the negative formal charge by induction is going to act to stabilize. So we're going to go ahead and add this to the list here, and then we're going to go into definitions of what we're referring to when we talk about induction. So delocalization of that negative formal charge. So much like with resonance, we're trying to spread the formal charge out or share it over multiple atoms. So we're delocalizing the negative formal charge over multiple atoms. And we're going to be using groups that are electron withdrawing by induction. So electron withdrawing by induction. And there's a bunch of new words here that we've embedded in this statement. So we need to go through what those different terms mean. So first off, when we think of the term induction, the way that you can think of induction is as the presence of nearby atoms that are going to allow the bond electron density to shift by polarizing bonds. So induction, by definition, and this is one of those big words that's going to come up quite a bit in the semester of organic chemistry, so it's important to get a grasp of what we're referring to when we talk about induction sooner rather than later. So induction is referring to nearby atoms. Atoms nearby, for example, are anion and the conjugate base. And those are going to be nearby atoms that shift electron density within the molecule by bond polarization. So they're going to shift what regions of the molecule are electron rich and electron poor through the polarization of bonds. So you're probably familiar with the idea that if we have an atom such as a carbon bonded to an electronegative atom such as a chlorine, that individual bond is polarized. That it's polarized such that the chlorine, the more electronegative atom, takes the lion's share of electrons from the covalent bond to become negatively polarized. And the carbon, as a result of that, has to lose some of its electron density, so it becomes positively polarized. That would be described as bond polarization across just one bond. Induction we can think of as a polarization effect across multiple bonds. So in the case of induction, groups that are electron withdrawing tend to be electronegative atoms. Electron withdrawing means that the atoms are going to draw electron density toward themselves and away from the rest of the molecule. So when we talk about groups that are electron withdrawing means they're pulling electron density toward themselves and away from the rest of the molecule. So when we say something's electron withdrawing by induction, we're referring to groups that polarize bonds by pulling electron density toward themselves and away from the rest of the molecule. So groups that polarize bonds by pulling electron density toward themselves. So there's going to be groups that are defined as being electron withdrawing by induction. And examples of groups that are electron withdrawing by induction are generally going to be electronegative atoms. So examples of situations where groups would be electron withdrawing by induction would be if we had, hypothetically, a carbon chain here and at one end an OH group. That electronegative oxygen atom is going to be electron withdrawing by induction because it's an electronegative atom. So it's going to not only pull the electron density from this bond in green toward itself, but that effect is going to extend into additional bonds down the chain as well. And the effect of induction does drop off with the number of bonds. So more bonds that separate the electronegative atom from whatever other part of the molecule we're focusing on, the more bonds there are, the lower the inductive effect that is going to take place. And typically we consider induction to be effective up to about 3 bonds or so away from the electronegative atom. So, and as it gets further and further away, the inductive effect drops off. So groups that are electron withdrawing by induction are going to tend to pull electron density away from the rest of the molecule and toward themselves. On the other hand, groups that are electron donating by induction are going to do the opposite. They are eager to get rid of some electron density, and so they're going to push electron density away from themselves and toward the rest of the molecule. So electron donating groups, and it's important that we make the distinction here because not all induction is the same. There's groups that are electron withdrawing by induction and groups that are electron donating by induction. So that's we're defining both of these here. So groups that are electron donating by induction are going to be defined as groups that polarize bonds by pushing electron density away from themselves. So electron donating groups are going to push electron density away. There aren't too many groups that are defined as electron donating by induction. In terms of organic chemistry, the groups that are most commonly recognized as being electron donating by induction are going to be alkyl groups, that is carbon chains. So alkyl groups, that is just carbons that are sp3 hybridized, and the associated hydrogens with them tend to donate electrons by induction. So those are described as electron donating groups. So in the case of looking at our situation of stabilizing a conjugate base and applying this concept of induction towards stabilizing conjugate bases, in order to stabilize a conjugate base, we want to be able to delocalize or move around the negative formal charge, because the negative formal charge is the unstable site of the conjugate base. And so in order to allow us to share or delocalize that negative formal charge, we need groups that are going to withdraw electrons by induction. In other words, we need groups that are going to pull electron density toward themselves and away from the rest of the molecule. Because if we have a negative formal charge somewhere in the molecule, in order to help share that negative formal charge, we want to pull that negative formal charge away from where it starts at and pull it to somewhere else in the molecule. And so induction is that bond polarization that allows that to happen to some extent. And again, induction is generally going to be less important than resonance if we had to rank the relative contributions of these, because in resonance, the formal charge is literally completely shared over two atoms. We can show resonance structures that will move the negative formal charge from one atom to another. In induction, we're just polarizing the bond, so it's a more subtle effect than resonance. So we can generally say that induction is going to be less important than resonance in the vast majority of cases because it's just polarizing the bond. So it's sharing the electron density and redistributing it a little bit, but it's not completely allowing the negative charge to be totally shared over multiple atoms. It's a more subtle effect than resonance is the way that we can think of it. So let's take a look at a couple of example problems of how we can use this concept of delocalizing the negative formal charge by induction as a way to differentiate between the strengths of different acids. So let's look at, as our example problem here of delocalizing a negative formal charge by induction, we're going to ask the question of which is going to be the stronger acid. So which is the stronger acid? And we're going to take a look at these two structures. We're going to take a look at one that is chloroacetic acid. So it has a chlorine atom there. And we're going to compare that to just acetic acid. And we're going to ask which of these two is the stronger acid. In other words, which one has a lower pKa value. So in each of these two cases, what we need to do to assess this is we need to write out the conjugate base that would result from deprotonating each of these. And in each of these cases, these examples are similar to the carboxylic acid that we worked with earlier, where we had a similar COOH group. And when we deprotonated, we created COO-. I'm going to do the same thing here. Rather than writing out the complete reaction, it's going to be this proton on the OH group that gets lost. That's going to leave us with O- right here. And our other conjugate base is going to correspond to having an O- at the corresponding position right here. So we need to compare the stabilities of these two conjugate bases, and then we go through this list of ways to stabilize conjugate bases. if we went down the list, what we'd see is that the electronegativity of the atoms that have the negative formal charge is the same in both cases. The resonance is the same in both cases, where we could share the negative charge over both oxygen atoms. And so that brings us down the list to induction as what we can look at here. And so we need to think about what's different between these two conjugate base structures and whether the groups that are there are electron donating or electron withdrawing. So if we look at and compare over here, we have just a CH3. We classify that as an alkyl group. Carbons and hydrogens is part of a chain here. And this group is going to be electron donating by induction. So it's trying to push electron density away from itself and toward the rest of the molecule. And the problem with that in terms of stabilizing this is that we already have a region over further right in the molecule that's already too electron rich because it has that negative formal charge, meaning it's got more electron density than it wants. And so if we have additionally electrons that are being pushed over there from this methyl group, the CH3 group, the alkyl group, that's going to tend to destabilize this conjugate base. On the other hand, if we come over to the other side, our chlorine atom over here, we recognize as being electron withdrawing by induction because it's an electronegative atom. So this is going to withdraw electrons. And what we mean when we say it withdraws electrons is it's going to pull electron density toward itself and away from the rest of the molecule. So it's going to pull electron density from over here, pulling that electron density this way, and therefore it's going to be able to delocalize or spread out and share a little bit of that negative formal charge over multiple atoms. So that is going to stabilize this conjugate base relative to the situation on the right where we had instead a CH3 group that would be trying to donate electrons. We want a group that withdraws electrons to stabilize anions. So we're going to go ahead and say that this is the more stable of the two conjugate bases, and therefore the original acid that corresponded to it would be the acid that is the stronger acid. So the stronger acid, the acid with the lower pKa, is the one that has that chlorine atom on it because it's going to give way to the more stable conjugate base there. So we really can think of having two ways to delocalize electrons, move electrons around within the molecule, those being resonance, where we can show with different structures that we can actually physically move the negative charge, or in the case of other types of molecules, run into move the positive charge. But we can move the charge from one location to another within the molecule completely. So we can totally share the charge over multiple atoms. That makes resonance a stronger factor than induction, where we're just getting a more subtle polarization effect of multiple bonds in induction by groups that are so-called electron withdrawing, meaning those are electronegative atoms, or electron donating. The electron donating groups we typically run into are alkyl groups, that is carbon chains or carbon rings where the carbons are all connected by single bonds. So as our last point that's going to act as one of our criteria for stabilizing or destabilizing conjugate bases, onward to point 5 here in our list of factors that stabilize and destabilize conjugate bases. Factor number 5 is going to be that increasing the percent S character of the atom that has the formal charge, the negative formal charge, is going to cause that conjugate base to be more stable. So we're going to go ahead here with step 5, increased percent S character is going to stabilize this conjugate base. And this factor is typically only considered when we're looking at and comparing two atoms that are identical. So comparing two nitrogen atoms that are in different hybridization states, one being sp2, one being sp3, for example, and things like that. So increased percent S character stabilizes the conjugate base, and use this guideline only for comparing the same atoms. So comparing two different carbon atoms or something like that. So we're only going to use it to compare two of the same atom. So for example, two carbon atoms, two nitrogens, two oxygens, etc. So let's take a look at this as applied toward looking at carbon atoms. So as our example here, we're going to look at the relative acidity of an alkyne. That's a molecule that has a carbon-carbon triple bond relative to the acidity of an alkane, so CH3, CH3. So in each of these cases, what we're going to do is go ahead and write out the conjugate base that would result from deprotonating each. So if we bring in our base to attack, we come in, grab a proton from there, CH bond breaks. That's going to give us our equilibrium arrow, and we'll have BH as our conjugate acid. And we'll have our carbon-carbon triple bond, and that carbon is going to have a lone pair of electrons that it picked up from breaking that carbon-hydrogen bond, negative formal charge on it, and we'll do the same thing over here for CH3, CH3. Base comes in, grabs one of those three hydrogens, and I'll show one of those three hydrogens explicitly here so we can show the bond breaking. So that CH bond explicitly. Base comes in, grabs that proton, breaks the carbon-hydrogen bond, and leads us to our conjugate base here. So CH3, CH2, lone pair electrons on the carbon, and we'll get BH out of that as well, our conjugate acid. So we're comparing the stability of our two carb anions, our two negatively charged carbons, the one right here and the one right here. So remember that we can assign the hybridization state based on how many regions of electron density there are around a particular carbon atom. So in the case of the carbon atom on the right here, how many regions of electron density would we have there? So we have a total of 4 regions of electron density because we have 2 bonds between that red carbon on the right and hydrogen, 1 bond to the second carbon, so that's 3 bonds in total, and then as the 4th region of electron density, we have the lone pair of electrons. So therefore it has 4 regions of electron density, which means it has to be sp3 hybridized. On the other hand, we come over to the deprotonated alkyne, and we see just 2 regions of electron density there. We have the lone pair making up 1 region of electron density, and that triple bond making up the other region of electron density. So this would be an sp carbon. And we said that having an increased percent S character stabilizes a conjugate base. So how does that play into and work with this business of sp versus sp3? So if we look at and we think about the percent S character of an sp orbital, we can think of an sp orbital as being the same as having s to the 1 power, p to the 1 power. So in other words, there's a total of 2 there, because 1 plus 1 makes 2. And if one of those 2 total is S, because we said S to the 1, that means that 50% of the character is S character, because 1 out of the 2 total was S. We can do the same sort of thing over here for sp3. So sp3 is synonymous with saying S to the 1 power, p to the 3, which means we have 4 in total, meaning 3 plus 1. And of that 4 in total, only 1, because we do S to the 1, of the 4 is S character. So 1 out of 4 is 25% S character. So a higher percent S character corresponds to a more stable conjugate base, and therefore our deprotonated alkyne is going to be the more stable of the 2 conjugate bases. And so, since it's the more stable of the 2 conjugate bases, it has to correspond back to the stronger acid starting material. So our stronger acid is certainly going to be our alkyne. And if we were to look at a pKa chart of the pK of an alkyne versus an alkane with that carbon-carbon triple bond typically has a pKa value of around 25. So it's by no means a super strong acid, but an alkane has a pKa value of around 55. So certainly the alkyne is dramatically a stronger acid just due to this difference in percent S character between the 2. So if we were to order molecules in order from strongest acid to weakest acid amongst the hydrocarbons, molecules that have just carbon and hydrogen, we would see that alkynes that have a carbon-carbon triple bond are the strongest acids. Then second strongest are alkenes that have a carbon-carbon double bond, because those are sp2, and so they would have a 33% S character if you did the calculation. And then the least acidic of all are the alkanes. So the alkanes are going to be the least prone to losing a proton, period. They are very, very non-acidic. So with that, we can take these 5 criteria here that we went through, place the negative formal charge on the more electronegative atom, place the negative formal charge on the atom with the larger atomic radius if they're in the same group, delocalize electrons by resonance or induction, and maximize the percent S character as our 5 criteria that we can look at as ways to stabilize a conjugate base. And these are going to be the ways that will allow us to correspond back to what is going to be the stronger acid. And if we want to rank the relative importances of these, the most important of the factors is generally going to be to place the negative formal charge on the most electronegative atom. And it's fine if that happens through drawing a second resonance structure. That's even better because then you get some resonance and having the negative formal charge on the electronegative atom going on. But certainly, most important, place the negative formal charge on the most electronegative atom, or even better yet, have no formal charge at all. And then secondly, that resonance, assuming that it's really productive resonance, is another factor that we would rank really, really high on the list. And particularly if the resonance can share the negative formal charge over multiple electronegative atoms, that's going to be extra gold stars for the resonance being a factor to stabilize the conjugate base. The other features that we've talked about, induction, for example, is a more subtle effect that's not going to be as strong as having the negative formal charge on the most electronegative atom or having the negative formal charge moved around by resonance. And then the other criteria, placing the negative formal charge on larger atomic radius for atoms in the same group and that percent S character business, are some specialized rules that apply generally when you're just comparing two atoms that are the same. So comparing 2 different carbon atoms in the case of the percent S character, or comparing 2 atoms in the same group for the larger atomic radius business. So with that, you should have some guidelines in place for going about predicting what's going to be the stronger acid. And there's a bunch of practice problems in the worksheet that goes along with this concept for giving you some more experience at predicting which is going to be the stronger acid amongst the two. The last thing that I can mention here with regard to these factors that stabilize the conjugate base. So far, we've been using the term conjugate base, conjugate base, conjugate base, referring to the product side of the equation. We can also use these same criteria to determine and assess the relative strengths of different bases. So if we want to compare the strengths of bases, we can use those guidelines that we've just talked about above, points 1 through 5, in the same order of relative importances to look at the strengths of bases. So when we were saying conjugate base above, we were saying what stabilizes the conjugate base, et cetera, which is all well and good, but sometimes you might run into a situation where you're just given a base to start with. You're given 2 molecules that already have negative formal charge, and you ask which of those is going to be the stronger base. So to determine the strength of bases, use the criteria above. So that was those steps 1 through 5 that we wrote in red just above. And then, and I should really be saying above there rather than both. I don't know why I said both, but use criteria above. And keeping in mind that the strong base is an unstable base, and the weak base is the stable base. So those criteria that we looked at above for stabilizing bases are going to be what leads to stable, going to be what leads to weak bases. So weak base equals a stable base. And those criteria we looked at above in points 1 through 5 were all criteria that would lead to a stable base. So you can use those criteria to compare the relative strengths of different bases. So for example, just to lay this out here, if we had 2 different molecules, so we have, this should be reading in H in A. So we had this structure versus, we'll go ahead and do O in A. So if we look at these 2 molecules, what we need to recognize straight away is that when we have a bond between sodium and sometimes at the far right side of the periodic table, such as nitrogen or oxygen, it's definitely going to be an ionic bond between those two. So we actually have, in reality here, when we dissolve this, we're going to have a cation and anion situation. So you have NH, and that nitrogen has to have two sets of lone pair electrons to account for all the electrons, the valence electrons that are there. Sodium is going to have a positive charge, nitrogen has a negative charge. And then similarly, we can do that process over here, putting a negative formal charge on the oxygen. That oxygen has to have three sets of lone pair electrons. Sodium is going to be +1. And if we take a look at those two structures, we can ask ourselves when we're assessing which of these is the stronger base, we have to ask which is the less stable and which is the more stable. So we're going to be comparing the nitrogen anion to the oxygen anion here, and which of those is going to be the more stable of the two. So looking at these, oxygen and nitrogen are not in the same column of the periodic table, so we can't compare atomic radius. They are not going to be able to engage in resonance because there are no resonance structures we could draw here for either of these to move the negative formal charge around. They both have an alkyl group attached to them, a carbon chain. So there's no difference in induction there. So what we look at is the difference in electronegativity between the atoms. Oxygen is further to the right-hand side of the periodic table. Therefore, it is more electronegative. And because it's more electronegative, it is better able to handle that negative formal charge. And hence, this is the more stable of the two bases. And by being the more stable of the two bases, that means that it is going to be the weaker of the two bases. Weaker meaning less reactive. It's very happy as is relative to the nitrogen anion. So in fact, if we're looking for really, really strong bases, which later on in the semester we're going to need some super strong bases to do some of the reactions that we're going to try to carry out, we will need things like nitrogen anions present in order for the reaction to take place. So with that, we'll conclude this particular lesson.